So now, ladies and gentlemen, the next thing that we are going to look at is reaction rate example. So now an example of the reaction rate. So look at it here. We have a reaction where butane chloride react with water to produce butanol plus HCl. So this is a plot of concentration. This is the concentration versus the time for the reaction. And this yield a curve like this. So you see, this is initially at time 0. Look at the concentration of the reactant. So the concentration of the reactant, which is butyl chloride, is 0.11. So as the reaction progress, the concentration of the reactant also decreases. Look at it. It is now decreasing down here. The concentration of the reactant decreases. So now look at the concentration. It is decreasing down with time. So if you want to get instantaneous time, for you to get instantaneous time now, you can get rates at this point, that is at time 0. And also you can get rates at 600 seconds. How do we get the rates? Now you get the value of, you know that from, this is a normal graph. So from the graph, and this is a y-axis. So you can have your y2. You can have your y2 here. You can even also have your y1. So this one can be your y1. So you have your y1 and y2. And of course, if you move down here, you have your t1. That is your first time. You have your t1. And you have also your t2 here. You have your t2. So if you want to get the instantaneous rate at this point, then you now take the concentration is 0.1, then minus 0.06. And the time here is 200. So 200 minus 0. So it means that it's the same thing to say, for you to get instantaneous rate at this point, you will now say y2 minus y1 divided by t2 minus t1. If you can have this one, it means that at this point you can now calculate the rates here. And your y1 is 0.1 minus 0.06 divided by 200 minus t1, which is 0. So 200 minus 0. So at this point, you can now calculate your rates. So this is a typical example of how to get rates. Okay. Then, so the slope of a line tangent to the curve at any point is the instantaneous rate at that point. So this is instantaneous rate at this point, and this is also another instantaneous rate at this time. So this is at time 0, and this is at 600 at 600 seconds. Okay. So you see the rate generally slows down with time because the concentration of the reactant decreases. Yeah. So with time, the rate decreases with time as the concentration goes down. So meaning that the instantaneous rate at time 0 and the instantaneous rate at 600 seconds may not be the same. So it means that the one at 0 will be higher than the one at 600 seconds. because as it moves down, the concentration decreases. So therefore, the rates will be different. So at time 0, the rate will be higher than at time 600. So now in the reaction, the ratio of butyl chloride and butanol is 1:1. Yeah, of course, look at it. We have 1 mole of butyl chloride here and 1 mole of butanol. So the ratio is 1:1. So now, thus, the rate of the disappearance of butyl chloride is the same as the rate of the appearance of butanol. So remember that the rate can be measured by the disappearance of the reactant. That is why here is negative with time and here is positive with time. So now the next thing that we are going to look at is rate law. So concentration and rates. Each reaction has its own equation that expresses its rate as a function of the concentration of the involved species, e.g. it can be reactant, product, or catalyst. So this is called its rate. So the rate has its own equation and it expresses its rate as a function of the concentration of the involved species. So but usually in the chemical kinetics, the rate law is usually considering the function of the concentration of the reactant, not the product and not the catalyst. So we'll now look at some example. So in general, the rate of the reaction increases as the concentration increases, since there are more collisions occurring between the reactants. So the overall concentration dependence of reaction rate is given by the rate law or rate expression. So the reaction follows simple rate laws. So you see, this is a reaction where you have your reactants and the products. So rate law is generally, the rate is directly proportional to the concentration of the reactant species, where K is constant, and here it means that you have the concentration of A and B. A and B are the reactant concentration. So that is why I said the rate law usually depend on the concentrations of the reactant, not the products. So the exponent here, we have exponential M and N is the reaction order for a specific reactant. And the key here is the rate constant. So if you want to now get the overall order, is the sum of the reaction orders. So if you sum M plus N, you will have your reaction order. So now the most important thing that we need to understand here is that the rate law usually expresses the concentrations of the reactant with some exponential, and to get the overall order of the reaction you have to sum the exponentials. And one very important thing that we need to understand here is that the rate law can depend or may depend on only one reactant or two of the reactants. So the determination of rate laws, how do we determine the rate law? So now look at it. In this equation, we see that determination of the rate law, rate constant, and orders are determined experimentally. So generally, by mere looking, you cannot say that you cannot give the real expression of a rate law, because it's only determined experimentally. So the order of a reactant is not generally related to its stoichiometric coefficient. So we need to understand a balanced chemical equation. Now look at the balanced chemical equation here. The balanced chemical equation of oxochlorides here is 2, but the rate constant or the rates no, sorry, okay, the order of the oxochloride here is 1, but not 2. So remember that the order of the reaction and the rate constant can only be determined experimentally. You cannot just say that the overall order of the reaction is this based on the stoichiometric coefficient. Is not possible. So look at it here. The chloride, the oxochloride here is 2, but if you look at it in the uh, expression of the rate law is 1. Okay. So now reaction with simple rate law. So look at it. We have hydrogen react with iodine to produce 2 hydrogen iodides, and we have trioxochlorate, oxochlorate to give us trioxochlorate, and the minus 2 molecules of chloride. So you see that the order of the reaction of oxochloride is 3. Sorry, is 2. Sorry, yeah, is 2. But you see that the stoichiometric coefficient there is 3. Okay. So now the reaction with complex rate law. So this is some examples of the reaction with an expression of rate loss. So now always follow simple rate loss. So you see, this one we call it unimolecular decomposition. We have A and B. Remember that the rate law usually depend on the concentration of the reactant. So you see that the expression of this rate law is K times concentration of A. Then for the bimolecular reaction, we have A plus B. So it depends on the concentration of A and B. But here we have the concentration of A and B, sorry, A and A. So that is why we have K times concentration of A times concentration of A, and we have Ka square. So reaction order reflects molecularity. So the reaction order is called molecularity. If it is 1, it is unimolecular. If the reaction order is 2, is bimolecular. So you see, these are the 2 examples of bimolecular reactions, because the second and the third, which is this one and this one, they are all bimolecular. Why? Because the reaction is depend on the concentration of the 2 reacting molecules. I think for this, we are going to stop here.